If we're going to perform linear regression, we need to be able to have a kind of a general way of approaching this. So what I have here is a table with years and percent, the percent of Americans without health care in each corresponding year. So in 1987, 14.4%, 1990 has 15.7%, 1993 has 17.2%, and 1996 has 17.6%. So now we need to enter the data into our graphing calculator. And then we create a scatter plot to see if a linear model is even reasonable. The data should follow a linear pattern with no distinct curvature. I'm going to make X be the years since 1987. That means that instead of the particular years, now we're going to end up having 0, 3, 6, and 9. So now graphing that on my scatter plot, I can see my 4 ordered pairs here. And if I look at that closely, it looks like this data follows a linear pattern. Now, there might be some slight curvature to it, but even in those cases, since lines are so easy to work with, often what we do is we just kind of ignore it and go with a linear pattern. Now we go ahead and use technology to get the equation that is the best fit for the data, and we graph the unrounded linear equation and the data points to see how well it fits the data. In this particular case, I'm using a function p of x for percent, and that's equal to 0.3700x plus 14.5600. And you can see that this line goes very close to the points. The first point is a little bit low. It goes almost perfectly through the second point. The third point is a little bit high, and the last point is a little bit low. So the last thing we need to do is go ahead and report that equation and the numerical results in a way that makes sense in the context of the problem, with the appropriate units and with the variables justified. So I would say that the best fit line to 2 decimal places is p of x equals 0.37x plus 14.56, where x is the number of years since 1987 and p of x is the percentage of Americans without health care. Now that we have that line, we can use it to answer some questions. So according to the model, what will be the percentage without health care in 2000? So what I notice is that the year 2000 corresponds to x equals 13. So substituting that value into our model, we get p of 13 equals 0.37 times 13 plus 14.56, and that's approximately 19.37. So that means in 2000, approximately 19.4% of Americans were without health care. According to the model, in what year did that percentage reach 16%? So the value 16% is a value for our function p of x, so we're going to set p of x equal to 16% in the model and solve it for x. So that leaves us with 16 equals 0.37x plus 14.56. So if I subtract 14.56 from both sides, that leaves me with 1.44 equals 0.37x. And if I divide both sides by 0.37, I end up with x is equal to 1.44 divided by 0.37, which is approximately 3.9. So remembering that x was the years since 1987, that means toward the end of 1990. Now the last thing to talk about here is the coefficient of correlation. If our data is perfectly linear, which rarely happens with real data, then we don't even have to worry about how good is the fit, because it'll go through all the points. But if the data is not perfectly linear, the coefficient of correlation is used to measure the fit. So the correlation coefficient is a number that measures how well data points fit a linear model. And a graphing calculator can also display the correlation coefficient, but it's called R in that case. So the correlation coefficient R is a number that ranges from -1 to 1 that measures the strength of the linear relationship. The closer the absolute value of R is to 1, the stronger the relationship. If R is equal to 0, then there is no linear relationship at all. If you have a positive value for R, that means that the output values increase as the inputs increase. In other words, your line has a positive slope. Negative values for R mean that the output's value decrease as the inputs increase, or that you have a negative slope.